I will talk about a very important inequality related to the characteristic function of a random variable. So we have a random variable, which is x, and this is the characteristic function phi of u. It is given by this expectation of the exponential of I ux, and of course I is the square root of -1. U is a real valued parameter. The characteristic function is defined for any type of random variables, and it is bounded. So if we take the magnitude of the characteristic function, then it is the magnitude of this expectation e to the I ux. And by the triangle inequality, this is upper bounded by the expectation of the magnitude, and x is real valued, u is real valued. So this is a complex quantity. On the unit circle, the magnitude is unity. So this is expectation of 1, which is 1. So regardless of the random variable x, the magnitude of the characteristic function is less than or equal to 1. The characteristic function is always defined for any random variable. This is not the case for the moment generating function, because the moment generating function is different. It is expectation e to the tx. So it does not have this I. And so the moment generating function may be defined only for a range of t values, or for something like the Cauchy random variable, it is only defined for t equals 0. Otherwise, if you try to evaluate this expectation for t not equal to 0, basically it does not exist. So because of this, the characteristic function is used in convergence analysis, specifically when we study convergence in distribution. And in many cases, we need to upper bound this difference. So this difference is the difference between the characteristic function of random variable x and this summation. So this summation is, it has n plus 1 terms, iu to the k over the factorial of k. So it looks like it is derived from the Taylor expansion, and it is. And then here we have the moments of the random variable x. So we have basically when k is 0, this is 1. When k is 1, this is the first moment. When k is 2, that's the second moment. And we have all the way to the nth moment. So the magnitude of the difference is upper bounded by an infimum of over this parameter delta from 0 to 1. And the upper bound will involve the absolute moment of x of order n plus delta. So n, that is this n here, we have it here, plus delta, which is a number between 0 and 1. And then we have the beta function. So this is the beta function. And the beta function, so beta of w and z, it has several integral representations. One of them, which will be relevant to us, is an integral from 0 to 1. Then you have t to the power w plus 1, 1 minus t to the power z plus 1. So this is w. Here we have w plus 1. Here is z. We have z plus 1 dt. So the result of this integral is basically encoded by the beta function of these two parameters. Okay, so we want to prove this result. And again, because this summation, it's coming, or it looks as if it's coming from the Taylor expansion. So we will start with the Taylor expansion. So let me write the general formula. So if we have a function g of x, and so we'll assume that it is n plus 1 times continuously differentiable, then we have here a summation k from 0 to n, and then we have, this is my notation for the kth derivative, so I will use this x of 0. So this is the kth derivative of g evaluated at x0. And if the superscript is 0, then we are talking about the function itself. So this is at x0. So this is the point about which we are doing the expansion over the factorial of k, then x minus x0 to the power k. And then we have a remainder term. So the remainder term is what gives, the difference, the discrepancy between this g of x and this summation. Our function, because the characteristic function, it has this exponential I, so it is a complex valued function. And it is useful here to use the Cauchy integral remainder term, which is given by 1 over the factorial of n. And then we'll have an integral from x0 to x. And then we have x minus t to the power n. And then we have, so this is the n plus 1 derivative of g of x at t dt. Okay, so this is Cauchy integral remainder. And we will use g of x equal to e to the I u x, and x of 0, we will take it to be 0. So note that the derivative here, g, the kth derivative of this function is I u to the power k e to the I u x. So e to the I u x. Again, this is not surprising. We are using this particular function because if x is a random variable and we take the expectation of this function, that's the definition of the characteristic function. So this is equal to summation k from 0 to n. And then we'll have the kth derivative evaluated at 0. So the exponential is 1 over k factorial. And then we have x to the power k. And from here we have 1 over n factorial integral from 0 to x. Then we have x minus t to the n, then I u to the power n plus 1, then e to the I u t dt. So the difference, e to the I u x minus summation k from 0 n I u k over k factorial x to the k. This difference I will take here I u to the n over n factorial 0 to x, x minus t to the n d e to the I u t. And so we'll do integration. We'll do integration by parts. And so this is I u n over n factorial x minus t to the n e to the I u t 0 to x. And then we have minus, and we have integral. Let me copy those first, I u n over n factorial. Then we have integral from 0 to x. Then we have basically the derivative of this guy. So this will give an n. And then because there is a minus t here, so this minus becomes a plus. And then we have x of minus t to the n minus 1 e to the I u t dt. Now, if we put t equal to x, this is 0. If we put t equal to 0, then we get x to the n. So this will be this term, and then we have plus iu to the n over n minus 1 factorial, because we have this n here, integral from 0 to x of my x minus t to the n minus 1 e to the minus iut dt. Now, what if we take this term but without the exponential? Okay, so this is like sort of an experiment. What if we take iu to the n over n minus 1 factorial, and we integrate 0 to x minus t to the n minus 1 without the exponential? So this will be iu to the n minus 1 factorial. And then this guy will give 1 over n, then x minus t to the n. And then because of the minus sign, we have this. So this is iu to the n, these two guys, n factorial. And then when we put a 0, we get x to the n. If we put the x, we'll get 0. So this is what we have here, is this term without the minus sign. So now we have e to the iux minus summation k from 0 to n iu to the k over k factorial x to the k. This is equal to iu to the n over n minus 1 factorial. And then again, this term here can be represented by the negative of this integral. So I can combine the two integrals, and we will have x minus t n minus 1, and we have e to the minus iut minus 1. So this minus 1 is what will give this term, and then we have dt. Then we have okay. Now x can be positive or negative. I mean, so x is a random variable. It can be, for example, a Gaussian random variable or any random variable that can take negative values. So x can be positive or negative. So what if x is negative? Okay, so we need to also think about this. So if x is less than 0, then we can write down this integral. So it's 0, integral from 0 to a negative number. I can basically write it as minus the integral from x to 0, and x, it's a negative number, so I can write it as integral from minus the absolute value of x to 0. And because x is negative, I can also write it here as minus absolute x minus t to the n minus 1, to the n minus 1. And then we have e to the iut minus 1 dt. Then if we have, let's say, t tilde is equal to minus t, so do change of variables. So this minus, and then when t is minus absolute or absolute value of x, this becomes absolute x. This is 0, and this is minus x. Minus t becomes plus t tilde. And this is n minus 1. And we have here e to the I minus t tilde minus 1 and then minus. And so we have this is equal to, I have two minus signs. I can use one of them here and the other to have the integration from 0 to absolute value of x. Then I can take here minus 1 to the n minus 1 and here absolute x minus t tilde to the n minus 1. And then we have here e to the minus I u t tilde minus 1 d t tilde. Now, if x is positive, we can write down this integral. Okay, so if x is greater than 0, then x is equal to the absolute value of x. So this is iu to the n over n minus 1 factorial 0. I can write it like this, right? So I put here absolute x minus t to the n minus 1. And here we have e to the I ut minus 1 dt. So if you look here, you will find that the integral, when x is negative, basically we have this term, minus 1 to the n minus 1. And for this exponential, rather than having a plus sign, we have here a minus sign. Okay, so keep this in mind. Let's go back here to this expression. And now we want to get our characteristic function. So we need to take expectation of both sides. And since our ultimate goal is to have a bound, on the magnitude of this difference, so what we'll do is that we will take expectation. We will here take expectation and then take magnitude. Okay. So when we take the expectation, we will get, so take expectation, then magnitude. Then expectation will convert the exponential into phi x of u, right? So this will become the characteristic function itself. Now, when you take the expectation, now the summation will involve the moments of random variable x. So I need to have expectation of x to the power k. And then we have magnitude here. And this is equal to the magnitude of the expectation of the right-hand side. Okay, so here we have the right-hand side. And then by the triangle inequality, this is less than or equal to the expectation of the magnitude of the right-hand side. Like this. Now, this is the right-hand side. So what is the magnitude? Okay, so the magnitude of the right-hand side of this equation will be magnitude of u to the power n over n minus 1 factorial. And then we will have the magnitude of the integral. So this integral here, or we can write it in this form if x is negative. So this is, again, there is the triangle inequality for integrals, which means that the integral of the, if the magnitude of the integral is upper bounded by the integral of the magnitude. So this is u to the n over n minus 1 factorial. And then we'll have the integral now from 0 to absolute x. And then we will take the magnitude of what we have inside. So see that t is between 0 and t is between 0 and the magnitude of x. And also here, so this is a non-negative quantity. When you apply the magnitude, this minus will go away, and this guy will go away. And so we will have absolute x minus t. This is raised to the power n minus 1. And then, so this is this term raised to the power n minus 1. And then we have the magnitude of e2 plus or minus I ut minus 1 dt. So this is the upper bound. Okay, so this is what we have. And why plus or minus? Because if x is positive, we have this thing. If x is negative and we do these steps, then we will get a minus sign here. Okay, and again, when we take the magnitude, this guy, the magnitude of this guy is 1, and we end up with this upper bound on the magnitude. So what is an upper bound on this term here? Okay, so we'll take magnitude, generally e to the I theta, and theta is in R. So we don't care whether theta is positive or negative. Minus 1. I can write down this as e to the I theta over 2 plus I theta over 2 minus e to the I theta over 2 minus I theta over 2. That's this one. Then we can take the I theta, e to the I theta over 2 as a common factor. And then we have e to the I theta over 2 minus e to the minus I theta over 2. Then the magnitude of this product is the magnitude of the first term. And this is equal to 1. That's the number on the unit circle. And then we have the magnitude of the other term. And then by Euler, this is exactly equal to 2 times I, and then sine of theta over 2. And so this is, of course, the magnitude of I is unity. And so this is 2, and then the magnitude of sine theta over sine theta over 2. Now I can claim that this is upper bounded by 2 magnitude theta over 2 to the power delta, where we can choose delta to be any number between 0 and 1. So I am saying that the magnitude of, or the absolute value of sine of z, okay, and here z is real, is upper bounded by the magnitude of z to the power delta. So this is clear if basically the magnitude of z is greater than 1, or equal to 1. So we should be interested in the case in which, what if the magnitude of z is less than 1? Okay. So why is this inequality true? For example, we can apply the mean value theorem to sine. So I can say that sine z minus sine 0 over z minus 0 Okay, so what is this? So by the mean value theorem, this is equal to the derivative of sine of z, which is cosine of z, evaluated at a point between 0 and z. And since this magnitude, the magnitude of cosine zeta, is less than or equal to 1, then we have the magnitude of sine z over z is less than or equal to 1. Okay, if z is not equal to 0, and then we have the magnitude of sine z is less than or equal to the magnitude of z, as we have. Okay, now if magnitude z is less than 1, then magnitude z to the power delta is greater than okay, and make it from 0 to 1. Magnitude z to the delta is greater than the magnitude of z. So we have a number. If this number is between 0 and 1, and we raise it to a power, and this power is between 0 and 1, then we get this inequality here. Okay, so so we can, you know, put that this is, so if magnitude z is less than 1, this is less than or equal to magnitude z to the power delta. So what is the importance of having this delta? Why not just, you know, use magnitude sine z is less than or equal to magnitude of z? You know, delta is a parameter, and this parameter will allow us to basically manipulate our upper bound. So it is a parameter that we can use, for example, to get a tight upper bound. So if you look here to the inequality that we are trying to prove, now once you get an expression and it's parameterized by this delta that lives between 0 and 1, so for every delta that is between 0 and 1, this term here is an upper bound, then you can say what is the least upper bound. And so you can take infimum over delta in the closed interval from 0 to 1. So this delta again is a parameter that allows us to get the least upper bound. And in some cases, we can just assign specific values to delta, and we are happy to work with those upper bounds without the need to take the infimum. Okay, so it depends on the proof that we are working on. So sometimes it's just we can take this upper bound and set delta equal to 0 or delta equal to 1 or any specific value of interest in this interval from 0 to 1, if basically this is good enough for what we are doing. So now we have this e to the plus or minus iut minus 1. So based on our result here, this is upper bounded. So after changing it to this quantity, so we have a 2. So this will be upper bounded by 2, and then the magnitude of ut over 2 to the power delta. So this is 2 to the power 1 minus delta, and then magnitude u to the power delta, and then magnitude t to the power delta. Magnitude t to the power delta. Okay. So let's now combine what we have. We have the magnitude of phi x of u minus summation k from 0 to n I to the u to the k over factorial of k, expectation of x to the k. This is upper bounded by an expectation. So this is upper bounded by an expectation. And inside the expectation, we have 2 to the power 1 minus delta magnitude u to the power n plus delta. So we have n from here, and we have here delta. And we, in the denominator, we have the factorial of n minus 1. Then we have an integral from 0 to the absolute value of x. And then we have absolute x minus t raised to the power n minus 1. And then we have absolute value of t. Inside the integral is non-negative, so I can just write this as t to the power delta. And then we have dt. And this is x. Let's do change of variables. Z is equal to t over absolute x. When t is 0, z is 0. When t is absolute x, then z is equal to 1. Here, absolute x, t itself is z by absolute x raised to the power n minus 1, z to the delta, absolute x to the delta, and dt is absolute x dz. And this is equal to integral from 0 to 1. We can take absolute x as a common factor. It will be raised to the power n minus 1. We have a delta here. We have a 1 here. So this is n plus delta. And then we have 1 minus z to the n minus 1. And we also have z to the power delta dz. This guy can be taken outside. So x n plus delta, and then we have integral 0 to 1, then z to the delta, 1 minus z to the n minus 1. And this is an integral that can be expressed in terms of the beta function as I introduced it at the very beginning. So specifically, this is beta, and then we take this power and add 1, comma, this power, and you add 1, which is n. So now we have I x of u minus this summation iu to the power k over k factorial expectation of xk. So an upper bound on the magnitude of this difference between the characteristic function and this sum of n plus 1 terms is, so we have from here 2 to the power 1 minus delta magnitude u to the power n plus delta over n minus 1 factorial. And now don't forget that we need to apply the expectation operator. It will be attached to this absolute value of x raised to the power n plus delta. And then we have beta delta plus 1, comma n. This is an upper bound. And this is true. This is true for every delta. That is between 0 and 1. So basically, we can get the least upper bound by taking the infimum of the right-hand side with delta between 0 and 1. And this is basically the result that we needed to prove. Now, the special cases of delta equal 0 and delta equal 1 are, are very useful. So sometimes we do not really need to do the infimum or anything. Let's see what if delta is equal to 0. That's a specific value of delta. We will have, so the upper bound becomes 2 absolute value of u to the power n over n minus 1 factorial. Now we have, so this is the nth absolute moment of x. And then we have beta of 1, comma n. The beta function is basically gamma, gamma of 1, gamma of n over gamma of n plus 1. Gamma of 1 is 1, gamma of n is n minus 1 factorial, and gamma of n plus 1 is n factorial. So in this case, the upper bound becomes 2, absolute value of u to the n. And then see, this n minus 1 factorial will go with this one. It will be replaced by n factorial. And then expectation of absolute of x to the power n. Okay. And if delta is equal to 1, the upper bound equals, so 2 to the power 1 minus 1, that's 1. And then we have u to the n plus 1 over n minus 1 factorial. We have the power here will be n plus 1, but then we have beta of 2 and then n, and this is gamma 2 gamma n over gamma n plus 2. Gamma 2 is the factorial of 1, which is 1. Gamma n is n minus 1 factorial. And then gamma n plus 2 is n plus 1 factorial. So here in this case, we will have n plus 1 and over this n minus 1 factorial will be replaced by n plus 1 factorial. And then we have expectation of x to the power n plus 1. Okay, so let's now write what we have. So this is our fundamental result, that if we take the characteristic function of random variable x, which is this expectation, minus those n plus 1 terms, which are derived from the Taylor expansion, k over k factorial. And here we have the moments of x from k equals 0 to n, that the magnitude of this difference is upper bounded by the infimum of delta between 0 and 1 of 2 minus 1 delta un plus delta over n minus 1 factorial. And then we have an absolute moment of x of order n plus delta. And then we have this beta function, which is delta plus 1 comma n. But again, sometimes it is just more convenient to use the specific cases of delta equals 0 or delta equal 1. And so this is also, this infimum is upper bounded by the minimum. And if we put delta equals 0, then we have here 2 u of n over n factorial, and then expectation of x to the power n. And if we put delta equals 1, then we get absolute value of u to the power n plus 1 over n plus 1 factorial. And then we have expectation of x, absolute value of x to the power n plus 1. And sometimes we can just, pick one of these two terms depending on what we are doing. Okay, let's finish this by taking special cases. Okay, so we can use this to generate many inequalities. So suppose that you take n equals 0. If you take n equals 0, so the magnitude of phi x of u, now if n is equal to 0, then this summation has just one term, and this term is just equal to 1. So this is the difference between 5x of u and 1. And recall that the magnitude of phi of xu is always less than or equal to 1. Now, if we want to have an upper bound on the magnitude of the difference between phi x of u and 1, now this is if we have n equals 0, so this is less than or equal to the minimum of, so it's 2, okay, which is not very useful, but it is what we get from this term here. If we put n equal 0, from here we will get u, and basically we have factorial of 2, which is 2, and then the expectation of okay, so here is an inequality that this is less than or equal to 1/2 the absolute of u, the expectation of the absolute of x. Suppose that x is 0 mean, and we take n to be equal to 2. So in that case, the left-hand side will be the magnitude of phi x of u minus, then the first term in the summation is 1. The second term will involve the expected value of x. So if x is 0 mean, so this term is gone. And then we will have plus iu squared over 2, and then expected value of x squared. So this is phi x of u minus 1 minus u squared over 2, the variance of x, because x is 0 mean, so its second moment is equal to the variance. And now this is upper bounded by the minimum of. Now we have n is equal to 2, so we have here again we will have the expectation of x2. So this is actually also the variance over factorial of 2, which is 2, or we have the other term will be u to the power 3. Then we have expectation of x cubed divided by factorial of n plus 1. So that's factorial, which is 6.